Okay, let's get this started. Hello, everyone. We're back again. Yeah, I saw that comment from Nat. I knew someone was going to comment like that based on Natalie's comment. Yes, new background. I was just going to mention that. I'm actually at the same table, but I have a lot of stuff working on the other side, so I had to move to the corner. So now I'm facing the wall. Yeah, so we are going to continue. That being said, one thing I do want to mention is that in a couple days, a day or two, you guys should be expecting an email regarding it's going to be an invite to the platform on which I want us to do those tests, long distance. So I found a solution, I think it works, we talked it over, and so I'm going to be uploading my roster to it and sending out invites pretty soon. So look out for that. It'll have instructions on everything that you'll need and how to get set up and all that good stuff. And I'll probably also actually run a practice test on that platform early next week, just for you guys to test it out. Just do a few silly problems. I don't know if I'll do a full-blown practice test, but maybe like just a couple questions, like what would be on a quiz, and you guys can take the test, upload your answers. Yeah, Top Hat is what we're using. So far for what I needed, and well, the solutions is still, the platform for proctoring is still in its beta phase. And so they're just getting into this game of online proctoring. They're more like a media kind of thing. They have their own textbooks and stuff like that. But they're just rolling out this stuff, and it's a pretty good solution. But at this point, it is also the best solution that I can get for free. So that's what we're going with. And it's pretty, I think it's going to work out nicely. But I'll send, you guys will get email invites. Yeah, I think you have to make an account for it. It's a new online platform. I'm not sure if it's going to force you to, but I think it's going to force you to like create an account and all that good stuff. Yeah, so look out for that. So Friday or Saturday, expect sort of an invite email, just inviting you to actually create an account on the platform. So I had that set up earlier today. Everything seems to go well. I'm optimistic about it, which is good. I haven't been optimistic about anything in a while with everything that's going on. So I think it'll be good. I think it'll be okay. So look out for that. That being said, let's actually just jump into it. We have a lot to cover here. So let me share OneNote. So there we go. Let's not worry about that right now, Mohammed. Why would it be low? You're all gonna be fine. Anyway, I know you're scared, but don't be afraid. You will be prepared. Like I said, you guys don't know about it. I mentioned this in my class yesterday. A practice exam is actually posted. So you will know what the exam looks like already. So I do recommend, it's already posted on the class website. So if you could just scroll down, that's where the syllabus is and where where are you supposed to quiz answers and all that good stuff, which that page hasn't been updated for a while because of all this thing. But there's a section called test reviews. There's now a review for test 1. So I would recommend that you actually follow the instructions. So it'll tell you, okay, here are the topics that are on the test. Take some time, study for them, and then take the test. So try to take the test as a real test. So it's a PDF file. You open the PDF file and just actually do it. Time yourself. Don't use any help, don't use any aids, just try to get through the test after studying. Pretend like you're studying for a real test. Take a day, maybe try the test tomorrow, and then see how it feels. And then based on that, you can actually go with a plan for next week. So yeah, there's a practice test up. Forgot to do that. I told my class yesterday, but I just remember that it wasn't set up on Tuesday, so you guys don't know about it. So yeah, try the practice test. Follow the instructions for the review of the practice test and that kind of stuff. I'll probably, and like I said, next week I'm going to roll out another practice, and that practice is mostly to just make sure that the platform is working properly for everyone. So that one is going to be like a test run, and we'll just actually have you log into Top Hat and actually do another practice test there, submit it, and actually make sure that you know what it's going to feel like come Thursday. Yeah, so those are the new developments in the testing realm. That, do I want to mention? I don't think. I think that's all I want to mention right now. Yes, don't panic is instruction number 1. Okay, all right. As always, just to make sure things run fairly smoothly here, I'm going to turn off my camera right now. You'll only hear my soothing voice explaining to you mathematics, and hopefully that will be good enough. So we are going to talk about the cross product today. That is the, well, we're going to spend about 2/3-ish of the class talking about the cross product, and then we're actually going to start the next section. Let's actually just jump into this. So as you guys might have remembered on Tuesday, we want to talk about things in 3 dimensions, and we realized that we needed a few things to get this to work. For example, we needed to find ways to dissect things into 2-dimensional objects, patches. We needed a way to measure the area of these patches. We needed a way to measure how these patches are tilted in space and have some notion of direction. And we also wanted our new notions to really coincide well with vectors, which we also introduced recently, last class, or the class before that. 2 people are still trickling in. Okay, so we discovered a couple things. We discovered some formulas that can help us determine the angle between vectors. We also determined the fact that if we want to find the direction of a patch, the best direction is a normal direction or an orthogonal direction, quote unquote. Orthogonal just meant perpendicular. So the best way to describe the direction of some flat plane floating in space is to talk about the direction that's perpendicular or orthogonal to that direction. And we talked about the dot product. This was a product of vectors that describes the angle between the vectors. And now we want to talk about the other one, the cross product. That's going to be the guy that's going to help us to find an orthogonal vector. So we also saw that for us to determine that a vector is orthogonal to some plane, we needed 2 vectors in that plane that aren't parallel. And we had to make sure that that vector is orthogonal to both of those vectors at the same time. So now we have the issue of how do we find a vector that is orthogonal, aka perpendicular, to 2 other vectors at the same time. The cross product is an answer to this concern. So let's actually find the vector, and I'm going to call out, you know, like Babe Ruth pointing to the stand before he hits a home run. We're going to call out the guy that we're going to find. We're going to put a target on him, and I'm going to tell you right now, we are going to find the guy that fits this description. Okay, so we have 2 vectors A and B. We want to find, and n is just a unit vector. Remember what unit vector means, it has magnitude 1. N is just a unit vector that's orthogonal to both A and B. The vector we care about is a scalar multiple of such a vector. So we are going to find a scalar, remember this here is a scalar, times n. So it's going to be parallel to that vector. And this is the vector that we're going to call the cross product. Now, as you can hopefully see from this definition and just comparing that to what we did last class, notice that what the cross product is, it is a vector that is going to be orthogonal to 2 vectors, and it will have the magnitude that is the area of the parallelogram formed by the 2 vectors. So remember when we had a vectors A and B, where see here. And hold on, technical issues. Trying to get my pencil to work. Okay, there we go. All right, So remember, if we have vectors A and B, you can imagine that there's a parallelogram that they will form. And if the angle here is theta, then the area of this region is magnitude of A, magnitude of B, sine theta, right? We saw that last time. So here's what we're going to do. We are going to find a vector such that it is orthogonal to both of these guys at the same time, and his magnitude is the same as this area. Now, why would we want the magnitude to be the same as that area? There are a couple reasons for this. Now, based on how we are going to develop it, this will be a natural consequence, but if some of you want a more intuitive feel for why the sine function would appear and all that good stuff, here's a link that of something that you'd want to actually watch in that regard. Not important. If you don't watch it, it's not a big deal. Just know that a cross product will have these properties. It will be orthogonal to two vectors at the same time, and its magnitude would be the area of the parallelogram formed by the vectors. That's just what a cross product is. That being said, I do want to emphasize the cross product is a vector. Okay, so if you take two vectors, the cross product is another vector. It is a vector that's orthogonal to both the vectors at the same time. Remember that the dot product was a scalar. The cross product is a vector. Another thing is that the cross product, as we're going to describe it, really only works in 3 dimensions. So a cross product in 2 dimensions doesn't really make sense. It'll actually be a magnitude in itself, which is not useful. The dot product is all that we need. A dot product can work in any dimension, but a cross product specifically, as we're defining it, will work only in 3 dimensions. There is a higher dimensional version of a cross product. This is called an exterior product or a wedge product. And that you can find out more information about that here. But once again, this is not necessary for you to read at all. And in fact, for pretty much everyone at this point, that is going to be way above your pay grade. I mean, it'll take like a couple years of really intense studying of abstract mathematics to even understand what these guys are. So you go there, you'll probably not understand anything on the page. But that being said, in 2 years, if you're still interested, come back here to that link and talk about the cross product in general. Our version is going to be the 3D version cross product. That is a specific instance of the exterior product or the wedge product. Okay, another thing that we can notice is that if we were to take the magnitude of the cross product, it'll be taking the magnitude of this. Since the magnitude of this n is considered to be 1, our magnitude just becomes this guy. And that immediately tells us a couple things. One, there's a sine theta magnitude here, which means that if your theta is something that would make the sine function 0, then the cross product is going to be the 0 vector, or the magnitude of the cross product will be 0. Specifically, theta equals 0 and theta equals pi will make the cross product a 0 vector, because here you would get 0 times a vector n. That will give you a 0 vector. What does that mean for us? Well, if the angle between 2 vectors is 0 or pi, it means that they are parallel. So we now have another way to think of vectors being parallel, which are these 2 ways right here. 2 vectors are parallel if their cross product is the 0 vector. They are also parallel if the magnitude of the cross product is the 0 scalar. These are both go hand in hand, of course. So just to recap on all these maxims that we definitely want to remember here. 2 vectors are orthogonal if the dot product is 0, right? So the dot product is a scalar. If it outputs the scalar 0, your 2 vectors are orthogonal. We know that 2 vectors are parallel if one is a scalar multiple of the other. That is the basic definition. However, it is actually the case, based on this definition, that if the cross product is the 0 vector, then the 2 vectors are parallel. That is a natural consequence of the definition. Okay, so cross product is the 0 vector means that the 2 vectors that you just took the cross product of are parallel. Okay, now another thing that we have to worry about, which cross product? Notice that there will be two vectors that are orthogonal to vectors A and B. So if I have A right here and I have my B right here, notice that I can have two vectors that are orthogonal. I could have one pointing in this direction at 90 degrees from A and B, but I can have one pointing in exactly the opposite direction at 90 degrees to A and B again. So there are two potential directions here. Now, for the sake of convention, so that all our answers look the same and everyone's math kind of agrees with everyone else's math, as long as we're all doing the correct thing, we're going to come up with a convention, kind of like PEMDAS. There's always a specific vector that we have in mind when talking about the cross product. And the one that we will have in mind is the one that obeys the right-hand rule. What is the right-hand rule? Let's talk about the right-hand rule. We're not talking about the right-hand rule from physics. We're talking, this is the right-hand rule for multivariable calculus. So the right-hand rule tells us which of the two possible directions we want. If you take your right hand, point your index finger in the direction of A, and have your middle finger be in the direction of B, and you stick your thumb up, that is going to be the direction of A cross B. Another way to look at the right-hand rule is just flatten out your hand, point in the direction of A, and then make a fist, such that your fingers will curl in the direction of B and stick your thumb up, and your thumb is the direction of A cross B. You will notice that if you wanted to find B cross A, you would literally have to turn your hand upside down to achieve that. And so A cross B is the negative of B cross A. But let's just make sure we know how to find A cross B. In this example here, which of these two vectors is A cross B? Is N A cross B or is minus N A cross B? This is where you guys come in. Okay, so we have a lot of minus N's, and minus N is the correct answer. Notice that if you can like put your hand up on the screen, your right hand, in order to point your right hand in the direction of A and curl your fingers to be in the direction of B, you need to have a thumbs down kind of orientation, right? Right. So you'll need to actually twist your right hand this way, right? So here your fingers would have been like this or something like that, pointing in the direction of A. Your fingers then curl around to the direction of B. And in order to do that, your thumb would have to point down. So it turns out that in this diagram, the minus N is the direction A cross B. Of course, the upward direction is B cross A. And that is, in fact, the negative of A cross B. Okay. So here is what our cross product is. And let's not worry about how to find this guy just yet. I just want you to fully understand what this guy is. Having two vectors, A and B, in this orientation, you can imagine that there's a parallelogram formed by them. The cross product is the vector that is perpendicular to both vectors at the same time. So there's a 90-degree angle between that vector and B. There's a 90-degree angle between that vector and A. And at the same time, the magnitude, the length of that vector has magnitude of A, B sine theta. Namely, it will have the magnitude of this parallelogram, the area of this parallelogram. And it also obeys the right-hand rule, right? So that's what a cross product is. A vector that's orthogonal to two vectors at the same time. Its length will be the area of the parallelogram formed by the vectors, and its orientation will obey the right-hand rule. Because there are two potential directions, you want to use the right-hand rule to determine which direction you specifically care about. Okay, so that's the guy. This is the guy we want to figure out. So let's see how we're going to figure out what that guy is. Okay, so first of all, there are a bunch of properties here that you should know take effect. Property 1, I just showed you guys that A cross B is the negative of B cross A, and that is just a natural consequence of the right-hand rule. To get the cross product to work out, your right hand will either have to point up or down, and 1 is just the cross product in the opposite order. So property like property 2 is one that you can kind of see in terms of area, because if you have a parallelogram and you scale one of the sides, then the area itself gets scaled by that factor. And so property 2 would make sense. So again, we can pretty much use this definition and all the principles that we're doing here, and we can derive all these properties. And we'll be able to derive all these properties by things that I'm going to show you in the future as well. But for now, know that all of these hold. To make some comments on the properties. Property 1 shows that the cross product is not commutative. So remember what commutative means. Commutative means the order does not matter. For cross products, it is the order actually does matter. I want you to realize that A cross B is not the same as B cross A. They are not the same thing. A dot product is commutative. A dot B is the same as B dot A. This is not true for the cross product. This guy is actually equal to the negative of B cross A. Okay. One thing I do want to call your attention to is something that's not listed here at all. And so we know that this is not commutative. Now, here's something that's not listed, the associative property. And I just wanted to be aware, it's not because they forgot to put it in the box, it's because it's actually not true. What is associative? Associative means if you have more than 2 of them, like an A cross B cross C, associative says if we do the first 2 and then cross it with C, or we do the last 2 and cross that with A, we would get the same answer. However, this is not true. So that's not true either, okay? So if you have multiple cross products in a row, it will actually matter what order you compute the cross products in, which means if you're ever in a situation where you need to do like 3 or 4 cross products, you need to indicate with parentheses which pair of cross products you want to actually compute first. So cross product is not associative. It's also not commutative. So you have to be very careful with your parentheses if you're ever in a case where you'll need more than 2 cross products. We are not going to find ourselves in that case very often. Something else that's not listed but should be obvious is the fact that if you cross anything with a 0 vector, you will get the 0 vector. If that's not obvious, what we'll cover later on should also make that obvious, but I'll just mention that as we're walking by. Couple more comments on the properties. The last 2 properties, these guys are actually super important. The 5th property, that's this guy here, number 5. This guy is called a scalar triple product, or a box triple product, or a triple scalar product, or a triple box product, etc. You get the idea. These guys are very important. The scalar triple product is actually the guy that if I were to take the 3 vectors and compute an expression like on the left side of property 5, what that would give us is the volume of this guy here. Now this object here is called a parallelepiped. And so a scalar triple product is actually a way to find the volume of a parallelepiped. And if you actually compute this and you get the answer is 0, which is a scalar, notice that this is a scalar because it's a dot product, it means that all these vectors lie in the same plane, and the volume of this parallelepiped, which is just a 3D version of a box, is going to be 0. So that's something that's worth mentioning. And that's actually going to be a connection that we'll talk about later. Another thing, the 6th property, we're not really going to discuss this at all, but you'll notice that that is a triple cross product. That guy is called, did I list it here? It's called a vector triple product. That actually gives you a vector. And what that is, it's actually useful in physics in something like Kepler's first law of planetary motion and things of that sort. But we're not going to worry about that. I just want you to know that property 6, it might be, the properties 5 and property 6 might look like totally random things, to some people, I just want you to know that these things actually do matter. We will specifically be using property 5. We won't be using property 6, but it is a thing, just so you know. It is used elsewhere. So with knowing what the cross product is and with knowing these properties, what we are now going to do is we are going to figure out how to actually compute a cross product. So if I give you two specific vectors, how do you actually get the coordinates of the cross product, right? Or the components rather. How do you actually find what this vector will specifically look like? And Ash is shouting matrices. We'll talk about that pretty soon. Right now, I'm actually going to derive for you the formula. Then I'm going to show you how we can use matrices to get the formula. Then we're going to do a bunch of examples of using the matrices to get the formula. So we're building things from scratch here. All right. Here is how something that's going to be important for us. We know how to express vectors in ijk notation. So let's see how ij and k behave under cross products. Notice in our 3D space, the x-axis, the y-axis, and the z-axis, these guys are actually all orthogonal to each other, which means that they can be cross products of each other, of pairs in the system. So, for example, if I take I cross j, if I do that, my right-hand rule, my thumb will point in the k direction. So it turns out that I cross j is actually equal to k, right? Now, all of these guys are unit vectors, and so their parallelogram will have area 1, and so the vectors, the cross product will have area 1. So we can actually figure out all of these are true. So I cross j, you'll get k. If you do j cross k, you'll get I. If you do k cross I, you'll get j. If you do j cross I, you'll get negative k. K cross j, you'll get negative I. I cross k, you'll get negative j. One way to remember that is to just remember this circle that you just list I, j, k around it clockwise fashion. And all these positive equations you can get by going around the circle clockwise. So I cross j will give you k. J cross k will give you I. K cross I will give you j, right? To get all the negative relationships, you go counterclockwise. For example, I cross k will give us minus j. K cross j will give us minus I. J cross I will give us minus k, and so on. So we can get all these guys, right? We're going to be using these guys pretty soon. Another thing based on what we said earlier, when two vectors are parallel, their cross product is going to be the zero vector. So this tells you if you cross I with itself, you'll get the zero vector because I is parallel to I. If you cross j with itself, you'll get the zero vector. If you cross k with itself, you'll get the zero vector. So if I take any one of these basis vectors cross product with themselves, I get 0. And if I cross product the basis vector with one of the other basis vectors, these are how those cross products actually work out. Okay, now that being said, let's actually figure out how to find the cross product of two vectors. So let's say I'm given two specific vectors. So A is A1, A2, A3, B is B1, B2, B3. How do we compute their cross product? Let's actually figure that out. Okay, so I want to compute A cross B. What that is me trying to compute A1I plus A2J plus A3K cross product with B1I plus B2J plus B3K, right? Now, what is that guy going to work out as? Well, now we want to talk about this is a sum of three vectors. That is a sum of three vectors. So you want to know, well, how would I deal with a cross product of a sum of vectors? Well, we have a property for that. According to this, property 3, cross products distribute across sums, which means I can just go through and do the distributive law here and multiply these guys out. And of course, remember, cross products are not commutative. So the order is going to matter. So anyone who's on the left must stay on the left in the cross product. Anyone on the right must stay on the right in the cross product. On top of that, I know property 2 tells me that the constants, I can move factor constants out. For us here, the A1, the A2, and the A3 are the constants. B1, B2, B3 are the constants. So what does this mean? I can just distribute. Take A1I and multiply out. I can factor all the constants out, put it in front, and then the vectors just maintain their order in the cross product. So if I take A1I, multiply by B1I, I would get A1, B1, I cross I. Plus, I would get A1, B2, I cross J. Plus, I would get A1, B3, I cross K. Now that is true because of I'm using properties 2 and 3. Now, of course, you have to multiply everybody out. So we're going to do the same thing with A2. Multiplying out A2, I would get, well, A2 times B1, J cross I. I would get A2 times B2, J cross J. I would get A2 times B3, J cross K. Then I'm going to do it for the last term, A3. I would get A3B1, K cross I. I would get A3B2, K cross J. I would also get A3B3, K cross K. Now let's actually find out what that actually gives us. So using these guys above here that I mentioned here, we can start to work some of these guys out. Now, first thing to note is that I cross I is going to be the 0 vector, which means that this whole thing is 0. Similarly, J cross J, that's going to be 0. K cross K, that's going to be the 0 vector. So those guys are not going to matter. What about I cross J? So now our I cross J, according to this, that is the same as writing K. And what about I cross K? Well, I cross K is minus J. What about J cross I? J cross I is minus K. What about K cross J? Joke. J cross K is going to be I. K cross I, according to this chart, that's going to be J. K cross J, well, that's going to be minus I. And that's everybody. So now let's actually write these guys out and let's group them together. So let's group the guys that are all attached to I's. And let's group all the guys that are attached to J. And let's group all the guys that are attached to K. All right, who has I's in them? Well, A2, B3. And minus A3, B2. Who has J's? Well, the J here is a negative. I'm actually going to write the negative outside here just to have it coincide with the formula that we're going to see earlier. So this is A1, B3 minus the other J's right here, A3, B1. Plus, who are the K's? Here's one, A1, B2 minus A2, B1. And this, ladies and gentlemen, is the cross product. So this is the vector A2, B3 minus A3, B2, comma, minus A1, B3 minus A3, B1, comma, A1, B2 minus A2, B1. This vector, ladies and gentlemen, is the cross product. So if I have two specific vectors, I can know specifically what the cross product is going to look like. This will be the vector that is 1, it's orthogonal to both A and B. 2, it obeys the right-hand rule. 3, its magnitude will be the same as the area of the parallelogram formed by A and B. Now, how do I know all these things? Well, we use the properties that we derived earlier to actually multiply this out and work it out. So everything I mentioned is kind of built in to what we want to actually accomplish here. So this will be a vector that obeys all those rules that I just mentioned. And yes, you guys do need to remember how to do this. You guys do need to memorize this, which obviously has its challenges. Who wants to memorize that whole thing? So there's going to be a mnemonic for remembering this formula, because ultimately you're going to have to use this formula every time you want to do a cross product. And this is using something that we call a determinant. Now, let's talk about determinants. Some of you may or may not have seen this before if you've taken linear algebra. Some of you might have done this in algebra class or whatever back in high school. So for your reminder for such people, and if you've never seen this before, I'm going to teach you right now what you need to know about determinants. And I will emphasize that we'll teach this on a need-to-know basis, right? So this is one time where I'm not going to explain at length everything. So it's not comprehensive. So determinants is a whole other thing, comprehensive. And if you want to know a lot more about determinants, what you can do is you can watch my Math 392 lectures where I talk about determinants. That will show you a lot. And if you watch my Math 346 videos, that will tell you even more about determinants. Determinants are a really big deal. But right now, I'm going to tell you how to find a determinant by one specific method in one specific variation of that method. And as far as Calc 2 is concerned, you do not need to know anything other than that. So don't even worry about what a determinant is or what it means. Just know how to compute one. And in that regard, I'm just going to tell you specifically how you can compute determinants. Let's just jump right in. Definition. A 2x2 determinant is a number denoted. So here's how we denote it. Straight bars. 2x2 means there's a rectangular array of numbers with 2 rows and 2 columns. And this number is defined to be A times D minus B times C. And so you just multiply guys along this diagonal, and then you subtract the product of guys along this diagonal. So that's the B times C, and that's the A times D, okay? This is called a 2x2 determinant. So for example, if I ask you, what is the determinant of 1, 2, 3, 4? Well, that's going to be 1 times 4 minus 2 times 3. That is going to be minus 2 is the answer. That is the 2x2 determinant of 1, 2, 3, 4. Any questions on that? Okay, cool. All right, let's keep going. Once you go higher than a 2x2 determinant, though, things get a little bit more complicated. So we are going to now talk about the 3x3 determinant. And we don't need to know any determinant larger than this. So we'll use, there's a method called Laplacian expansion. And I'm going to teach you how to do it along the first row. Now, in general, the method I'm going to show you can work with any row or column, but there are a few conceptual tweaks that you'll have to make that I don't want you to have to worry about. We're always going to do it along the first row. Here's how that's going to work along the first row. So it's a 3x3 determinant, which means it's going to have 3 rows and 3 columns. Okay. Now, what is that going to equal to? We make this definition, right? If we expand along the first row, so I'm going to worry about the guy up here. Here's something important. You put a plus sign associated with the top left corner. Always plus in the top left corner, always. And you alternate after. So B has a negative sign associated with it. C will have a positive sign. This will have a negative, positive, negative, positive, negative, positive, etc. Okay? Because those signs are going to be important. You're going to take a plus the first number, you're going to take a minus the second number, and you're going to take a plus the third number. Plus what? So moving along the first row, you have A, B, and C. You're going to take plus A, and you're actually going to multiply it by a 2 by 2 determinant. Specifically, and I'm going to tell you what these guys will have to look like pretty soon. So you're going to have plus A, you're going to have minus B, and then you're going to have a plus C. And inside each of these is going to be a 2 by 2 determinant. Now, which 2 by 2 determinant will you see inside each of those? So here is how that's going to look. You are going to start with the whole thing, right? So A, B, C, D, E, F, G, H, I. Now, when you're worried about the A, what goes beside the A, you're focusing on the A, you're going to block out everything in the row and column of A. This guy that's left over is the guy that you're going to put in here. So this will be E, F, H, I. Then you're going to do the same thing for the B, A, B, C, D, E, F, G, H, I. So focusing on the B, you're going to block out everyone in his row and his column. You will be left with this matrix here. And this rectangular array of numbers is called a matrix, but you don't need to know that. And you're going to put that in here. So inside here, you do the D, F, G, I. You're going to do it again for the C. So A, B, C, D, E, F, G, H, I. You are going to, focusing on the C, block out everything in that row and column. The guy that's left over here is the guy that you're going to put in the, between the absolute value signs here. So this is D, E, G, H. And now, ultimately, what that becomes is you do the 2 by 2 determinant for these guys. Okay, so you're going to have then A times EI minus FH minus B times DI minus FG plus C times DH minus EG. Okay, so let's actually do an example. I want to find 1, minus 1, 2, 0, 3, 1, 1, 1, minus 1. Just do some small numbers here so you can get the idea. I am going to expand along the first row. So what we're going to have is we're going to have plus 1 times, block out everyone in his row and his column, 3, 1, 1, minus 1. Minus a minus 1 times, block out everyone in his row and his column, 0, 1, 1 minus 1, plus 2 times, block out everyone in his row and his column, you are left over with a 0, 3, 1, 1. Okay, so it's plus this guy, block out everything here, you get 3, 1, 1 minus 1, minus this guy, block out everyone in that row and column, you get a 0, 1, 1 minus 1. Then plus this guy, block out everyone in that row and that column, 0, 3, 1, 1. Now you do the 2 by 2s here. So this is 1 times minus 3 minus 1, plus 1 times 0 minus 1, plus 2 times 0 minus 3. So this here is a minus 4, this here is a minus 1, this here is a minus 6. And so this determinant here is minus 11. Now we're going to do a lot more examples of this kind of technique. But hopefully so far you're at least following me a little bit. Any questions on this process so far? Are we all good? Are we kind of getting it? Now, those of you who have seen this before, now you're probably just as good as you were all those years ago when you did it. But if you've never seen this before, you might feel a little shaky on it. That's fine. It's one of those things where with enough practice, it'll become second nature. Eventually, you'll be able to just literally jump to like this line without even writing this out. And it'll be easier. Now, why did we learn to do this, right? Which again, not comprehensive at all. But these are the calculations that you'll need to know how to do. It will actually help us find the cross product. So here's how we can do this with the above. We may define the cross product to be, so if I have A cross B, what I can define this as is as a 3 by 3 determinant, where along the first row you would have I, J, and K. And along the second row, you would have the A's components. Then along the third row, you would have the B's components. And of course, we're mentioning where A is equal to A1, A2, A3, and B is equal to B1, B2, B3. Now, let's actually calculate this. So this gives A cross B. You see that expression, or you know you want to compute that expression. You're immediately going to write this down, I, J, K, A1, A2, A3, B1, B2, B3. And now we are going to do that whole thing about expanding along the first row. So I pick the first row with our I, J, and K. I know that this is going to be a plus, that's going to give me a minus, that's going to give me a plus. So now I'm going to have plus I, I'll write it at the back. I'll have a minus J times some determinant plus a K. I have to move the chat box out of the way here. Plus a K. Now what goes in here? Well, focus on the I, block out everyone in his row and his column. You have this 2 by 2 matrix left. Find the determinant. This times this minus that times that. A2B3 minus A3B2. Go to the J. It's a minus sign, which is the minus right here. block out everyone in his row and his column. You'll have A1B3 minus A3B1. Move to the K. This takes a plus sign. Block out everyone in his row and his column. You do the determinant of the 2 by 2 that's left over. This will give you A1B2 minus A2B1. And that 2 looks very weird. Let's rewrite that. And gasp. Same guy we had before. So if you go back up to this definition, whenever I plug in the notes, you'll realize that this is actually the same guy. And this is why I wrote the negative sign outside here, just so that it coincides with the formula that I'm going to derive here. But yeah, so that's the mnemonic. So let's actually do I have a specific, let's do an example in the meantime. We have some more examples to do later, but let's actually jump into one right now. Suppose A is equal to 1, 0, minus 1, and my B is equal to 1, 1, minus 3. Find A cross B. So if I go A cross B, what would A cross B look like? So if my goal is to find a 3-dimensional vector that is orthogonal to both of those vectors and whose magnitude is the area of the parallelogram formed by those vectors, and who obeys the right-hand rule, who is the guy that I would care about? Well, this is the guy that I would care about. I would immediately go into IJK. Line of the A, the guy on the left, 1, 0, minus 1. Line of the B's, the guy on the right, 1, 1, minus 3. And then I'm going to actually compute the determinant of this. Now I can just go into the component notation. And again, once you get a lot of practice with this, you'll be able to do it in your head, a lot of it. So in the I, block that out. You'll get 0 plus 1. J, you're going to have the negative of that. You're going to have minus 3 plus 1. And K, block that out. You're going to have 1 minus 0. So this is 1, comma, that would be minus 2 times minus 1, 2, 1. That's the guy. So if in this case I had A was that and B was that, then we just found this guy. So if my A was, if my A happens to be the vector 1, 0, minus 1, and my B happens to be the vector 1, 1, minus 3, then the vector that points in this direction, A cross B, is going to be 1, 2, 1. And so that is finding cross products using determinants of so-called matrices. Matrices are just rectangular arrays of numbers. Now, why would that work? Well, it turns out that, and we'll see this a little later as well, that a 3 by 3 determinant could actually be interpreted as the volume of a parallelepiped. Like, you can think of this as, if I have this here and this here. You can think of this as if I had 3 vectors. In space, then if I created a parallelogram with those guys, then the volume of this would be equal to 11, right? So you'll get the sign volume. It'll give you a positive or negative based on orientation, but if you want a positive volume, you just take the absolute value of this number, okay? So determinants are already kind of connected to areas of parallelograms and volumes of parallelepipeds. And again, if you want to know more about that, if you're interested, there's another course. You can watch my 346 lectures or my 392 lectures. But for now, knowing how to actually compute one is what's important, because we need to be able to do things like this. Given two three-dimensional vectors, you will often need to find another vector that is orthogonal to both of those vectors. This is how you would go about doing that. Right? And if we were to create like some parallelepiped here, some parallelogram, the area would be equal to the magnitude of 1, 2, 1. And so in fact, the area of this particular, the magnitude of this guy is radical 6. So yeah, that's how to compute a cross product. Let's do some examples. And then if anyone still has questions, they can actually ask me while we're going through these examples. Move these guys over here. All right, let's jump into this. Boom. Let's do cross product here. So we want A is 1, 2, 3. B is 3, 0, 2. What is A cross B? All right, I'll give you guys a minute. Tell me what the answer is. Go. No Wolfram Alpha or calculators or internet. Do this by hand. Ah, we have an answer. So someone thinks it's 4, 7, minus 6. So suggestion. Oh, someone else got the same thing. Got the same, getting a lot of I agrees. No one wants to be a contrarian here. No one wants to show up and be like, they're all wrong. Okay, let's actually, you can't disagree, Ash, it was your answer. Ash literally just disagreed with himself. Yeah, no, I disagree. All right. Okay, so let's actually see, is that the actual answer? Right. And this is where, especially if you've never seen this before, I really wanted you to actually practice this by hand. Don't just watch me, because it is something that is going to take some getting used to if you've never really seen determinants before or computed a cross product before. So yeah, you want to compute that, you set up this determinant. The visual setup is, and the visual and positional setup is very helpful. You're going to list the components of vector A, then list the components of vector B. You're going to take a negative sign of whatever's in the middle. So I block out everything in that row and that column. You'll have this box here, 2, 3, 0, 2. 2 times 2 minus 3 times 0. Then you go to J. You're going to take the negative of this, block out everyone in that row and that column. 1 times 2 minus 3 times 3. Then you're going to go to K, block out everything in that row and that column. You're going to have 1 times 0 minus 2 times 3. And so we get 4, comma, this is minus 7, but you take a negative of that, 7, comma, minus 6. And I suppose I also agree with the answer. Okay, so that's the answer. That's the vector. That vector is going to be orthogonal to both of these vectors. It obeys the right-hand rule, and its magnitude is the area of the parallelogram formed by those two guys. All right, any questions from anyone? Are we all getting it? What's funny? Oh, fun. All right. All right, let's move on. Find a vector that's orthogonal to the plane passing through these 3 points. So that's the next question. So we have a plane, kind of like our patch. There are 3 points in this plane. So I know one point in that plane is the point 2, 0, -3. Now I don't know positionally how they're arranged, but it doesn't matter. This is just a visual aid. 3, 1, 0. And here's another point R, which is 5, 2, 2. Give these prompts for bonus on the exam. Well, I don't know. We'll see. Right now, I'm in writing practice exam mode. I don't know what I'd give for bonus on the actual exam, but I might give some stuff like this. Because our exam goes up to the end of series. So since then, I actually have quite a bit of things I can ask you about already. Parametric equations, polar coordinates, vectors in general. Can ask you about dot product, cross product. There's a lot of material that I can squeeze into the bonus section, but I would much rather you focus on the other stuff right now. All right, so ideas on how to tackle this problem. Make a vector parallel to the plane, how? Make a vector using 2 points. Okay, which points do you want to use? P and Q. Let's make a vector P connecting P to Q. And so you have the vector PQ. All right. So how would you go about making the vector PQ? How do you make a vector connecting 2 points? Right, you take the final points minus the initial points. So it's going to be 3 minus 2, comma, 1 minus 0, comma, 0 minus a minus 3. All right, now what? Let's do P and R. So this would be P, R. And yeah, we can do P, R. 5 minus 2, 2 minus 0, 2 minus a minus 3. All right, now what? Then cross product for the perpendicular vector. So for example, if I wanted to find, it says find any vector. So let's say we wanted to find, let's say we actually want to find this guy. Who is this guy? The guy pointing up. What is this guy specifically, the one I drew? It's the other way around. So this is actually PQ cross with PR, right? The other, the one going this way is the other one. And that will give us what we need. So that's what we are going to do. So the vector we want is PQ cross PR. But the other way could work as well. I'm just, for definiteness sake, I just picked one. That's going to be IJK. I would have 1, 1, 3, 3, 2, 5. So in the I, 1 times 5, which is 5 minus 6, comma, J, 5 minus 9, comma, K, 2 minus 3, minus 1. This is minus positive 4 minus 1. So that's a guy. I have another example. Find the volume of the parallelepiped formed by A, B, and C. So we have like this thing where the three vectors A, B, and C. Say A, B, C. Right. So these guys we can just, now this thing isn't misbehaving. I don't know what, sometimes it does this. All right. Okay, so this A and C, and then B and C, and then da 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 da, and da 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 da, and da da da. Right. So might look like this. Don't know, but for illustration purposes, your actual results may vary. But this is essentially what we want the scalar triple product for. So the volume here is going to just be the magnitude, because the scalar triple product can return a negative answer. So this essentially you can compute by doing A dot B cross C. Now, it turns out that guy is going to look like the following. If you actually work it out, you'll realize that he would give you this guy. The components of A would go along the top. Components of B will go along the second. Components of C would go along the third. And a determinant, the whole point is to give you the signed volume of a parallelepiped. So the fact that the definition of the cross product is connected to matrices is actually not surprising at all in hindsight for anyone who's taken linear algebra. And yeah, so now for us, let's get specifically to the matrix we want. Where are we? So that I don't have to keep scrolling up. Okay, so A is 1, 4, minus 7. B is 2, minus 1, 4, C is 0, minus 9, 18. And now it's just finding this 3 by 3. And we only saw about how to expand along the first row, so that's what I'm going to do. So it's going to be 1 times minus 18 plus, what's 4 times 9? God, is that 36? Minus 4 times 2 times 18, which I think is 36, minus 0, plus a minus 7 times 2 times 9, minus 18, minus 0. So this is, is that 18 minus, well, 36 is 2 times 18. So this is 8 times 18 minus, well, plus 7 times 18. So we have 1 apple minus 8 apples plus 7 apples. We have 0 apples here. So what does that even mean? This means the vectors. So that's the volume. The vectors are coplanar. And we spoke about what that means up here. Coplanar, spoke about that earlier. That means they all lie in the same plane. So it actually doesn't look like a slanted box like this. It's actually flat. So they're actually just 3 guys in one plane. So you have just your A, your B, and your C. They're all in one plane. Yeah, and that does it for the cross product. That does it for this section. So now we know what a cross product is specifically. We know the properties it obeys, and we know how to compute it. So basically, if you remember how to compute it, you remember scalar triple products, and you remember the fact of what a cross product is, namely, given 2 vectors in 3 dimensions, we can find their cross product. The result of a cross product is another 3-dimensional vector, which has the following properties. It will be orthogonal to both vectors in the product at the same time. It will obey the right-hand rule, and it will have magnitude that's equal to the area of the parallelogram formed by the 2 vectors. Now, the orientation, whether you pick the one that's going to point up or down, is not going to matter for us much. It will matter in the next class. You would need to know how to pick a specific vector that's going to be a cross product, but for now we don't really have to worry about that. Usually finding either one is going to be fine. So even in that question where we did like PQ cross PR, for our purposes, if you did PR cross PQ, that's also fine. So I wouldn't, we don't have to worry about orientation, but that's it. Hopefully that's pretty okay. So we're actually going to move on to another section. We're not going to finish it, but we're going to start talking about some other things right now. In fact, we are going to talk about equations of lines and planes in space. Now, for those of you who just short that up, what do we need to know about equations of line? Okay, so let me start with that question. What do you guys think is the equation of a line? Faxi, write down the general form, equation of a line. What would you write? Y equals mx plus b. Yes, y equals mx plus b. Every school person old enough to find their own way home knows the equation of a line is y equals mx plus b. Ask any grade school kid. It turns out that this is wrong. This is no longer true in 3 dimensions. What? Yes. Let me give you guys let me give you guys the red pill right now. Let me give you some knowledge. Okay? Y equals mx plus b, the equation of a line, false. that is in your two-dimensional world. What we are going to do is what y equals mx plus b really is, because it turns out it's not a line, it's a plane. We saw this a couple lectures ago. Remember when I asked you guys, oh, draw in 3 dimensions what x equals 1 would look like, or what y equals 1 would look like, or what z equals 3 would look like. And we saw that these guys were all actually planes, right? Because they're only lines in the 2-dimensional space, right? Which we were seeing this whole time was just an intersection of the plane with the xy plane, right? So when you look at y equals mx plus b, you really only saw a shadow or a glimpse of what y equals mx plus b is. It turns out that that's what the matrix wanted you to see. There's actually a bigger truth behind it. That's what we're going to talk about now. So y equals mx plus b is actually not a line, it's a plane. Let's actually talk about lines, and we'll get to planes later on. So let's talk about line. So we just realized that in 3 dimensions, y equals mx plus b is actually not good enough. A good description of a line, it's equation of a plane, in fact. How would we go about finding the equation of a line? Now, there are a couple angles I could have gone with this, but I just want to get most straightforward way as possible. We're going to use vectors to figure out what it is. So let's suppose I had a line. Okay, now this is going to be a line in 3 dimensions. I'm just at a weird angle here right now. Okay, so boom, boom. See, when you do sound effects, it actually increases your writing powers. Okay, so here's my line floating in space. So this is the line going on for both directions. Now, the same way back in 2D, we can use some of our intuition here. To figure out a line, what you needed to know was a point on the line. Let's suppose I know a specific point on this line, x naught, y naught, z naught. And we had to know the slope, which is a description of the line. For now, description of the direction in which the line is moving. For now, because we're in 3 dimensions, a good descriptor of a line is of a direction in which a line is moving is going to be a vector. So let's imagine that there is a vector v that is parallel to the line. So this is v. It's parallel to the line. They're moving in the same direction as line. So I know a point and I know the direction in which the line is moving. So now the question is, if I wanted to find what is a description of an arbitrary point on this line, a variable point, right? Want to find a description of this, of finding this point. Want to know. Want to know how to get this. Here's what we're going to do in this regard. We are going to use position vectors. So suppose I have a vector that goes from the origin and hits the coordinate that I know about. I will call that vector R0, R0. And I have another position vector. This position vector is a variable though. And it is going to be the vector that hits the point x, y, z, which can move along this line. It's a variable. X, y, and z can vary. Call that R. Now, if I look at the vector connecting these two, so imagine that now I have a vector connecting these two. So boom, and it's running along this till it hits that point. Now, what is that vector going to be? Well, I know it's parallel to this vector, so it has to be a scalar multiple times that vector. So let's call it t times v. T is going to be the scalar that I'm using to measure it. Now, because I want to describe R, and I know these other two vectors, look at this picture. This should remind you of some that we've seen before, namely vector addition. If I take this vector plus that vector, I would get this vector. My R vector is actually equal to the R naught vector plus the vector t times v. That is the equation of a line. And in fact, that equation is so much better than y equals mx plus b, because in all dimensions, a line will obey a rule that looks like this. So once we know how to describe a line using vectors, it does not matter if I'm in 2 dimensions, 3 dimensions, or 18 dimensions, a line looks like this. Hence, we come down to here, the equation of a line. Right? What is a line actually? It's this equation. Now, if I start expanding on this, my R naught, I can think of as x naught, y naught, z naught. And my t, like if I think of the v as a, b, c, and I think of the r as x, y, z, then we have this version of the equation here, which I can combine those, I can add those into x naught plus a times t, y naught plus b times t, and z naught plus c times t. So I can describe a line as, this is called a vector curve. Now you're going to learn about that in the next class, but that is how to describe a line. Describe what the x, y, and z are doing separately. And notice that it will look linear in the first coordinate. So each coordinate would look almost like y equals mx plus b, but your t is the variable now. And that's your independent variable in the coordinates. So that is what a line actually looks like, at least in 3 dimensions. But a line is going to be a specific vector that indicates a point on the line, plus a scalar times a vector in the same direction as the line. Now, of course, we can equate the components. So my x is equal to that, my y is equal to that, and my z is equal to that. And then that leads me to this version of the equation of the line. I can just write it down a parametric equation, right? So this is the vector equation. It's describing it in terms of vectors. There's now a parametric equation for a line. So to describe a line, I have to tell you what the 3 coordinates are doing. Now, another thing that I could do is I could solve for t in each of these equations. I have here t is equal to x minus x naught over a. I also have t is equal to y minus y naught over b, and I would have t is equal to z minus z naught over c. And so since t is equal to all of these guys must be equal to each other, and then that leads us to this box right here. This is called the symmetric form of the equation of a line, and I'm not sure why this has a parentheses like that. And so that is called the symmetric form. Now, it's not very common to use this, but it's definitely common to use these 2 versions of a line here, a parametric form and a vector form. Now, sip some coffee here. You should know how to convert between these 2 and know how to recognize when you're looking at a line from when you're not looking at a line. And it's really just, it looks like one of these 2 sets of equations. Now, that being said, there is an issue here. You might worry about, well, what if one of the components of V were 0? So you can't divide by 0. In that situation, what happens is, if one of the variables are 0, then you actually just list that variable separately as the constant term, the x equals x naught, separate that with a semicolon, and you can write the other 2. So this notation is a little bit cumbersome. So we don't like using that. But if you ever see it in any source, you should know that this thing is also the equation of a line. Yeah, so this is how we can look at lines. All right, let's actually do some examples. So move this to the side. Move this to the side. Okay, so let's do some examples. Find the vector and parametric forms of the equation of the line through these 2 points, through the point 1, 2, 3, parallel to this vector. Okay, so here our x naught, y naught, z naught is equal to 1, 2, 3, and our v is equal to -1, 0, 2. This means that our line is going to be, write 1, 2, 3 as a vector. It's, in this case, it's equivalent to the coordinate because we're thinking of it as a position vector. Then t times that. And that's the vector form of the equation of a line. That's what a line looks like. Or you can even write it in another way. You can just combine, add those two vectors together. So this is 1 minus t, comma 2, comma 3 plus 2t. That's the equation of the line. Now this is, of course, the vector form. To find the parametric form, which we also asked about, you just set x equals this, y equals that, z equals that. So this means that your x is equal to 1 minus t, your y is equal to 2, and your z is equal to 3 plus 2t. And of course, your t can be anything here. And that's the parametric form. Any questions on that? So yeah, that's what a line looks like. So now you guys can all go mess with your little brothers and sisters and all these little kids going to school. So little Timmy, what do you think the equation of a line is? Tell you y equals mx plus b? Oh my boy, tisk tisk. Pat them on the head, wish them well for the future. Okay. Let me show you the real world, the real truth. Here's the red pill. Okay, let's get back on track here. I want to wrap up in a few minutes. I think we'll only give a... Okay, so find the equation of the line that goes through these 2 points. All right, so how do we do that? So in A, I have some line, don't know what it looks like, but I know that it passes through -1, comma 2, comma 0. And I know that it passes through 3, comma 1, comma 2. What I can do is, of course, create a vector that moves in this direction. And of course, I can create it using the points on the line. I know how to create that. So I would say that's 3 minus a -1, comma 1 minus 2, comma 2 minus 0. So that is my v. And then as my x naught, y naught, z naught, I can just pick one of these points. Now you could pick the other point, just so you know. It doesn't matter which point, it's any specific point. And so this means our line is x, y, z equals this plus t times this, comma, this plus t times that, comma, this plus t times that. Of course, here your t is in R. That's the equation of a line. B. Where does this intersect the xz plane? What do you guys think? Where does it intersect the xz plane? What do you know about the xz plane? Y is 0. Y is 0 in the xz plane. Y equals 0. Now, of course, for this particular line, I know what the y is. So this means that 2 minus t will be 0. In other words, my t will be 2. So this means the point of intersection is going to be, well, the 1 minus 1 plus 4t, 2 minus t, 2t, but then I evaluate that at t equals 2. So if I plug in 2 here, right, I just take this line equation. This is actually the equation that gives me all points along the line. So I know to hit the xz plane, I need my t equals 2. So I'm going to go here and plug in t equals 2. You're going to get 7, 0, and 4. So that's the point in the xz plane that this line will actually hit. C, where does it intersect this surface? X plus 2y minus 3z equals 5. C, intersection with x plus 2y minus 3z equals 5. Right, so again, I know what my x, y, and z are. My x is this, my y is that, my z is that. So this means minus 1 plus 4t plus 2 times 2 minus t minus 3 times 2t should be equal to 5. And I can solve for the t that's going to make this happen. So this is minus 1 plus 4t plus 4 minus 2t minus 6t equals 5. How many t's do I have? Well, minus 2t minus 6t, that's minus 8t, plus 4t, that's minus 4t. And then this is 5 plus 1 minus 4. So that's just 2. So this means that my t is minus a half. Now that's not the answer, that's just the scalar that I need to get the line to hit that surface. So what is that going to be? So this means point of intersection it's again going to be the minus 1 plus 4t, comma 2 minus t, comma 2t. But I'm going to evaluate that at t equals minus a half. So that is going to be plugging in minus a half here, I get minus 2, so that's minus 3. Plugging in minus a half here, I get 2 plus a half. That's 4 over 2 plus 1 over 2, that's 5 over 2. And here, plug in minus a half, get that. That's our guy. And we're going to wrap up with this example. This is going to be the last example here. Equation for the line segment. We actually spoke about that earlier. We saw this earlier. So since this is the second time, maybe I'll remind you, maybe this is a nice bonus problem. How to parameterize a line segment. So you want a line that connects to from this to that. And remember, you're just going to describe your X, Y, Z by figuring out where they start and what you need to add or subtract to get to where they end. So my X starts at 1. In order to get to -3, I need to subtract 4. So I attach a T to that. My Y starts at 2. In order to get to 0, I need to subtract 2, attach a T to that. My Z starts at 3. In order to get to 3, I need to subtract 3. No, I start at 3. In order to get to 3, I need to subtract 0. So that Z is always 3. So that is the line segment. And of course here, T goes from 0 to 1, forces it to be the line segment. When your T is 0, you hit 1, 2, 3. When your T is 1, you hit -3, 0, 3. Yeah, so we shall stop there for now. Now leave this question up in case you want to take a stab at it. So we'll start with this example next time, and then we'll actually go into planes, what a plane looks like. So you might want to try this on your own, but I think we covered a lot today, so we're going to wrap up there. So now that's what a line is. Hopefully there are no questions. As always, I am going to post this video recording of this lecture on YouTube, and I will post the notes in the description. If you have any issues or comments or concerns, I will address them in the next lecture, I guess. So I'll send out an email with all those details. So it'll be early in the week, like a Monday or Tuesday. Yeah. There is no review session. Your review is the practice exam. So you should look out for an email in a couple days about Top Hat. It'll invite you to create an account or whatever in the platform that you're going to use to actually take the exam. There is a review, a practice exam up on the class webpage right now. I would say go and practice that exam under the instructions, and we'll do a dry run on Monday and or Tuesday of next week. So maybe I'll, would this actually, yeah, in terms of times, I have to think about that because I don't really want to use up class time to do that. But yeah, that's what we're going to be doing. Yes, yes, that's the class webpage. Yeah, so you'll have extra time to upload your work. And again, all the instructions are going to be there of what you would need to be able to do that. And once you actually sign up, I think there's also an app, so you can just take pictures from your phone, scan it to PDF, and you literally just upload it from your phone into the app, and it'll go to me. And yeah, there's a lot of stuff to that will be described in that email. Office hours are 5 to 6 on Monday and 3 to 4 on Thursdays. Yes, it's in Zoom. So if you want to meet with me, you should like just email me and let me know, hey, can I see you in the office hours? And I'll send you the link to the room. All right. Anyway, guys, I'm going to have to run because I'm actually filling in for someone right after this. So I'm going to start another class at 6. I got to, get into a new frame of mind. And so I'm going to let you guys go. Again, watch out for this video. I'll see you guys. Stay safe. Good night. Have a great weekend. And I will look out for those emails from me. And I will see you guys in the next one. So bye. Later, everybody. Peace.